Great. Welcome to our final speaker session of the day before we move to the panel discussion. So I'd like to introduce Professor Sam Madden. He's a professor of electrical engineering and computer science at MIT's Computer Science and Artificial Intelligence Lab, for those in the industry, more commonly known as CSAIL. He's also a leader in an emerging field of big data and heads up the Intel Science and Technology Center for big data. So he's a real leader in this area, and I'm really looking forward, Sam, to some of your insights in this space to talk about outliers and data debugging, which from the previous presentations we had is a really, really key component of this whole artificial intelligence and machine learning space. So Sam, over to you.
Hey everybody, happy to be here today to talk about some of the work we've been doing. I'm going to talk really about some projects that we've built at MIT in my research lab that are focused around this problem. Broadly, we call data debugging, but I think it's really about thinking about how you identify anomalies and outliers in your data, and then try to sort of suss out the problems in your data, right? So I think that probably from the previous talks, you all have a sense of this, that, understanding when something goes wrong with your data, understanding what went wrong is really hard because you've got massive quantities of data and you've got these super complex pipelines and these sort of opaque deep learning black box models that run over the data. And so, something weird happens and you have to ask, what is it? What happened and why? Right. And that's kind of the goal that we're trying to address with these data debugging systems. So, one example that I'd like to use is if you imagine you're writing a mobile phone application, right? And you've got this runs on hundreds of thousands of devices out in the world. And, a problem that you have is that there are something like 25,000 different distinct models of Android phones in the world. So let's suppose you want to identify, what particular model of phone that isn't working well with our mobile application. You've got some complex machine learning pipeline. Maybe this is a, application to recognize, I don't know, animals with your phone, right? So this is thousands of lines of code, some complex machine learning pipeline, and you've got these 25,000 different Android models, and you have to figure out what is it about these different phones that are making some of them not work and some of them work, right? So there's this huge plethora of devices out there, and you have to sort of figure out, is it the fact that the Samsung phones that aren't working? Is it the phones that have a particular GPU that's not working? Is it the phones that, are running a particular version of Android that aren't working? Is it phones that have a particular setting on the operating system that's making them not work? So what is it that's making these phones not work? And so this is the kind of problem we're trying to address when we talk about data debugging. We've built a couple of different systems for doing this. One of them is called Dagger, which is a data pipeline debugger. So the idea in Dagger is that you have a big pipeline and you can, as you would when you're using a regular code debugger, you can in Dagger set what are called data breakpoints or assertions. So you can have this code essentially stop when it encounters some kind of anomaly in the data. And so Dagger is a way to take a pipeline of code and instrument it with these breakpoints. We also spent quite a bit of time building a system we call Macrobase, which is about explaining these kinds of anomalies, like which attributes of particular models of phones are the ones that have problems. And so the way that Macrobase works is that it identifies values that are anomalous, like the crash rate on this, on a particular subset of phones, and then it tries to isolate the properties of those anomalous values that are associated with the anomaly. So it says of the phones that have a high crash rate, it's the ones that are running Android 6.2 that have the problem, or the ones that are running Android 6.2 in Italy that have the problem, right? So it can do this sort of multi-dimensional search over the outlier values to find the properties, the things that are correlated with the outliers. And then the third system that I want to spend the rest of the time talking about today is a system we call AutoOD, which is a system for tuning outlier detection algorithms. So there's lots of these algorithms that identify outliers. We use them in Macrobase, we use them in Dagger. But one of the problems that we observed is that in practice, people who have to use these outlier tuning algorithms they're actually quite hard to use in practice. And so we're trying to make these algorithms much, much more accessible to data scientists and practitioners who need to use them in order to help debug their data. Right. So in order to understand that, let's I want to sort of take a step back and talk about what is an anomaly. Okay, so we just mean an object that does not conform to the expected behavior. Typically, this is some sort of an application-specific definition. Like, for example, devices that crash, right? That might be my definition of anomaly. Or it might be devices that just run my model really slowly. That could be another definition of anomaly. So typically, the idea is so the sort of way you might think about outlier detection is to say, well, I've got several different attributes like Samsung and Google and application versions, and I want to sort of think about these devices as some of them are failing, like you can see down here that a lot of the Samsung devices running version 2.1 are failing, and some of them are not failing, like most of the Google devices don't have failures. Okay, so this is the kind of context of anomaly detection. And what we'd like an anomaly detection algorithm to do is to sort of separate out, tell us which things are the outliers and which things are the inliers, to sort of automate this process of isolating the properties of the outliers for us. Okay, so I think probably the previous speakers have already motivated this. You guys understand that there's lots and lots of settings in which you might have outliers that arise, right? Like you can have outliers in healthcare. You might have people with very anomalous physical health readings that you need to detect and understand what is it about these people that's making them have these these unusual values, or in an Internet of Things kind of a setting, or a setting like what BT might have, where you've got lots of little devices that are connected to the world. You have some devices that are failing, right? You want to understand what is it about these devices that are failing? Is it that they're old? Is it that they're running a weird version of the software, et cetera? Right. And then finally, in a variety of online settings, you might have things like spoofing and fraud, where there's some set of anomalous things that you are seeing, like unusual transactions in a financial system, and you want to understand other certain properties of those transactions that are associated with being outliers. Okay, so that's the goal of an anomaly detection system. The problem with this is that that's all fine and good at a high level, but if you go out in the world and you say, okay, I need an anomaly detection algorithm, what you'll find is like 100 different academic papers that say, oh, here's the right anomaly detection, here's one, here's the other cluster you could use. I could, do some kind of regression. I could, fit a line to this, and I could say the outliers are the things that are far away from the line. I could do clustering. So I could divide the points into clusters, and I could say the outliers are the things that are far away from any cluster, right? So there's like, not, hundreds of papers, probably thousands of papers that propose different algorithms for doing these things. Okay, and each one of these algorithms, so not only do you have an algorithm selection problem, but each one of these algorithms has a set of parameters that govern their performance. So if I'm, running if I'm using regression to detect outliers, I have to say an outlier is something that is so far away from the regressed function that I fit to. Or if I'm doing clustering, I have to say, I have to define how many clusters there are, and I have to say how far an outlier has to be from any cluster to be an outlier. So there's all these parameters that govern the performance of these algorithms. And it's really, really hard to solve this problem. So one thing you might say is, could you just use sort of AutoML, right? Some sort of, sprinkle some magic fairy dust of like, automatic parameter tuning to just solve this problem. And it turns out that this what we found is that this doesn't really work great. And I'm going to tell you a little bit about why. Okay. And I'm going to talk about a method that we've developed that we think is a better way to sort of tame this, AutoML nightmare. Okay, so the sort of the state of the art today is you have all these different methods. They're governed by all these different parameters, right? And each one of these combinations of methods and parameters, we call this an anomaly detector, right? And a user in this setting has to basically somehow pick from amongst this pool of detection methods and settings of parameters, whichever one they think is best. So the onus is all on the user to make a right decision. Right. So what we might like to do is to try to automate this process. Right. So I might, so in a sort of, one thing that I might do is to, for example, think about a supervised method for doing this. So all these methods I've talked about here, where the user chooses them, they're sort of, we call them unsupervised because they don't require you necessarily to have a big training data set. I don't have to have pre-labeled a bunch of anomalies. An anomaly is just based on like how far away it is from some location in the data. An alternate view of this is I might say, well, let's treat this as a pure machine learning problem where it's like I've got supervised data, I have a whole bunch of labeled outliers, and I'm just going to learn a big fancy machine learning model to be able to classify things as outliers automatically because I have this training data set. Okay, so this is what AutoML would do. I could just, run some complex some algorithm that, automatically tunes the neural network architecture and the hyperparameters and, cranks out a machine learning model that can solve this problem. Okay, the challenge here is though this requires this labeled validation data set. Somebody has to have labeled what outliers are. And the problem is that outliers in practice are kind of rare. I don't necessarily have a huge archive of these outlier data sets that are pre-labeled. And so what we're trying to do in this auto ID work is to sort of be able to with a very, very small amount of human supervision, be able to sort of automate this process. So the idea is we're going to use a family of all these unsupervised anomaly detectors that don't require training data. I'm going to combine this with a very small number of samples, labeled samples that I'm going to use in order to test that, which of a set of candidate unsupervised anomaly detectors are best. So let me show you a little bit about how the method actually works. So the idea is that we have all these unsupervised detectors. We're not going to require the user to pick them. We're just going to we're going to try all of them, right? So we're going to say we've got this huge number of them. Let's try all of them. And what AutoOD is going to do is it's going to run all these outlier detectors on your particular data set. And it's going to figure out which data items these detectors all agree on, right? So if all the detectors say a particular data point is an outlier or not an outlier, then those detectors agree. Let's call those reliable labels. And then we'll have a bunch of labels which are kind of unsupervised, uncertain, like there's a lot of disagreement between the detectors. Okay, and so what we're going to do is we're going to actually train a supervised detector, okay, based on these reliable labels, okay, to be able to detect which things are outliers. And then we'll use that classifier to be able to classify the trained classifier we trained on the reliable labels to be able to to be able to assign labels to the things that we're uncertain about. Okay, and so we found that this general method is actually works surprisingly well in practice on real data sets. And it allows us to avoid this sort of problem of having to have this large set of manual labeled data. If I do happen to have a little bit of manual labeled data, I can include it, but I don't have to have a lot of manual labeled data in order to make this work. Okay. So again, the idea is identify the stable outliers and stable inliers. That is where all the detectors agree, and then use that to deduce a set of reliable labels. As a part of this, we also can prune out the anomaly detectors which don't work very well, because if there's an anomaly detector that disagrees with all of the other detectors on the uncertain result, then after we've trained this classifier, then we can sort of throw it out. So as a part of this process, we actually also refine the anomaly detectors to get down to a small set of anomaly detectors that are good ones for the problem that we have at hand. All right, and so we just repeat this process in a loop. I won't go through the details of how it works, but I'll just say that the algorithm that we've come up with is substantially better than the best detector. Okay, so this we're showing here a bunch of benchmarks for outlier detection. So people have built these outlier detection benchmarks. The black bars are showing the performance of our and the x-axis here is increasing the size of the data set from small to large. The black bar is the best performing manually selected detector, where you go through all the possible detectors that are there, all their possible settings of parameters, and you choose the best one. Okay, so this is this LSCF is the sort of previous state-of-the-art in automatic anomaly detector tuning. So our algorithm, AutoOD, you can see is actually better than the best detector in almost all of these data sets. So it's better than the best manually selected detector because it's effectively learning a combination of detectors that work really, really well for the data. And it's really substantially better, like by a F1 measure of accuracy, it's like 40 out of 100 points better on average, many of these data sets. And it especially works well on the really larger data sets where this problem is even harder. So we think this is really, really cool. And we're, we think we feel like this is a key part of any of these sort of data debugging problems. So just to wrap up, we built a bunch of these auto anomaly detection systems at MIT, and I talked about one, specific sort of algorithmic approach we took called AutoOD that helps people sort of select the right anomaly detection algorithm for their data. So we'd love to work with any of you who want to try this out on some of your data. I know we've already had some preliminary conversations with some folks at BT. So thanks very much, everyone. Look forward to the panel coming up. Happy to take some questions.
Great, Sam. Thank you very much for your insights on that. I've been madly scribbling down a few questions for the panel session here in a few moments. And Sam, just a reminder for you, you got to drop off the Zoom call and come back in on the Teams call for the panel discussion, just in case you'd forgot that at the end of the day. So yeah, thank you very much for that. So I'm going to start to bring this session to a close. Once again, some fascinating insights about the auto detection capability. Hopefully I'm going to have some really intelligent questions to ask these guys in a panel session. So I'll bring this to a close. And if you want to participate and listen in on the panel session here in a few minutes, click on the link on Feed Loop and we'll see you there in a few minutes. Thank you.